A linear transformation is quite an abstract thing. So in this lecture, we're going to develop a concrete description of linear transformations using matrices. The idea is as follows. So let's say we have a linear map T from a vector space V to a vector space W. Suppose also that we have a basis V1 up to Vn of V. Well, if I know all of the images of these basis vectors, so if they're given to me somehow, then I can compute T of any vector in V. So just by knowing the images of the basis vectors, I can use that to find T of any element of the vector space V. The reason I can do that is because that basis V1 up to Vn is in particular a spanning set, so I can write V as a linear combination of V1 up to Vn. Let's call the scalars involved A1 up to An. And when I've done that, T of V by linearity is equal to A1 T of V1 plus A2 T of V2 up to An T of Vn. So just by knowing the images of the basis vectors, I can compute what T does to any element of V. That means to describe our linear transformation T completely, it's enough for me just to give a description of what the images of these basis vectors are. But we can actually go one step better than this. If we have a basis for W, let's say W1 up to Wm, then we can express any element of capital W as a linear combination of that basis. So each of our images of the basis vectors V1 up to Vn of V could in turn be described as linear combinations of our basis for W. That means we can completely describe a linear transformation T from V to W using the following data. First of all, a basis for V and a basis for W. And secondly, the scalars needed to write each image of a basis element for V as a linear combination of the basis vectors for W. So we'll call the coefficients involved in this Aij. So this data naturally assembles into a m by n matrix, and that's how our description of linear maps via matrices and choices of bases is going to work. So here's the formal definition. We take a linear map T from V to W, we choose a basis, which I've written as B here, for V, and we choose another basis for W, called C. Then we notice that T applied to a basis vector Vj can be written as a linear combination of the W's, and so we define the scalars Aij to be the scalars that we need to do that. So the scalars Aij are the ones which we need to write T of Vj as a linear combination of the W's. Then the matrix of T with respect to initial basis B and final basis C, which we write like this, is defined to be the m by n matrix consisting of those scalars Aij. So this seems like a complicated definition, but I claim that it's actually very simple if you just remember what's going on. So as a way to summarize this definition, what you would say is the jth column of this matrix, T upper B lower C, records how to express T of Vj, the jth basis element from the basis B of V, as a linear combination of the elements of the basis C. Let's notice now why the order of a basis matters. If you change the order of a basis, then the matrix that you're going to get would have its rows or its columns in a different order. So this is why it's important for us that bases are sequences, not sets. It's because the order makes a difference to which matrix you get when you use this procedure to find the matrix of a linear transformation with respect to a pair of bases. So to try and convince you that this definition is a little bit easier than it looks, let's do an example straight away. We will take T to be the linear map from r squared to r cubed, defined by T of a vector xy in r squared is 2x plus y, 0, x minus y. I think that's very close to an example that we've looked at before. In any event, you can check by hand that this genuinely is a linear map. We will take a basis B for the domain of T. So B will be the standard basis for r squared. So I'll call that E1, E2, where E1, as usual, denotes the first standard basis vector, and E2 denotes the second standard basis vector. We will let C, our basis for the codomain of T, again be the standard basis for r cubed. So to avoid confusion, I'll call these basis elements E1 prime, E2 prime, and E3 prime, because otherwise I have two different things both called E1. But I still mean the standard basis. So E1 prime is 1, 0, 0, E2 prime is 0, 1, 0, and E3 prime is 0, 0, 1. We're going to try to work out the matrix of T with respect to the initial basis B, the standard basis for r squared, and final basis C, the standard basis for r cubed. So let's think what this should look like. Well, first of all, what shape should it be to begin with? It should be m by n, where m was the dimension of the codomain, and n is the dimension of the domain. So that means it should be a 3 by 2 matrix. So let's write this down. It's going to be 3 by 2. Now we'll draw a grid so we can see that this really is a 3 by 2 matrix. Now let's think what the parts of this matrix actually mean. So if you look at the definition of the scalars aij, well then, if you look at T of Vj, that's equal to the sum from I equals 1 to m of aij wi. Right, so the scalars on the right are the entries in the jth column of your matrix, because I is varying, so you're going down the matrix, whereas j is fixed, so you're looking at all of the elements a1, j, down to amj, so that is the jth column. So as I said, the jth column of this matrix is recording how to express T of the jth basis element for the domain as a linear combination of the basis elements for the codomain. So let's write that in. So we have the first column should be telling me about T of E1, and the second column should be telling me about T of E2. And what they should be telling me is how to express those things as a linear combination of the elements of the basis C, which are E1 prime, E2 prime, E3 prime. So I'm just labeling the columns and rows here. They're not part of the matrix. They're just labels to help us remember what's going on. So that first column should be telling me, how do I express T of E1 as a linear combination of E1 prime, E2 prime, and E3 prime? Well, let's work it out. T of E1, that's T of the matrix, the vector 1, 0. So in the definition of T there, x is 1 and y is 0. So what I'll get is 2, 0, 1, which is 2 times E1 prime plus 0 times E2 prime plus 1 times E3 prime. So the first column of my matrix should be 2, 0, 1. Let's now do the second column. The second column tells me about T of E2, and specifically how to express T of E2 as a linear combination of the basis C for my codomain. Now this time you should pause the video and work it out. All right, let's continue with this then. So T of E2, E2 is the vector 0, 1. So in the definition of T, I put x equals 0 and y equals 1. So I get 1, 0, minus 1 as my output, and that is 1 times E1 prime plus 0 times E2 prime plus minus 1 times E3 prime. And that means the entries in my second column of the matrix will be 1, 0, minus 1. The coefficients of the vectors E1 prime, E2 prime, E3 prime, which made up the basis C of the codomain of our linear map. So there's our first example of a matrix of a linear map with respect to two different bases. Let's now try a more abstract example where we have a linear map defined by differentiation. So this time our linear map D will be a map from the space of all real polynomials of degree less than or equal to 3 in the variable x to the same vector space. And the definition of the linear map will be d of f is df by dx. So this is the differentiation map. We're going to choose just one basis, b, of our vector space, and that'll be the basis consisting of the constant polynomial 1, then the polynomial x squared, and then the polynomial x cubed. And the question we'll try to answer is, what is the matrix of this linear map D with respect to initial basis B and final basis B. So again, what I have to do in order to work out the entries in this matrix is to compute the image of each of the basis elements under the linear map D and to express that image in terms of the basis elements for the codomain. And actually, we're using the same basis for the domain as we are for the codomain this time. Both bases are going to be this basis B. So let's start by thinking about what should the size of the matrix be. So matrix of D with respect to initial basis B and final basis B. Well, this time the basis of my codomain and the basis of my domain both have size 4. So in general, the matrix should have the number of rows equal to the dimension of the codomain and the number of columns equal to the number of basis elements for the domain. So in this case, that's 4 by 4. So let's write that down. Just first of all, I'm going to draw the grid lines in so we can see clearly that this is a 4 by 4 matrix. And let's remember what the columns of the matrix tell us. The columns of the matrix tell us about the images of the basis elements for the domain under the linear map D. So the first column is telling me about D of 1, the next telling me about D of x, the next about D of x squared, and the last one about D of x cubed. And what those columns record are what are the coefficients of the basis for the codomain, which you need to express D of 1, D of x squared, and D of x cubed in terms of the basis of the codomain. So those rows should be labelled by basis elements for the codomain. In this case, 1x, x squared, and x cubed. So let's work out those entries. To work out the first column, I work out D applied to the first element of the basis of my domain. And I express that as a linear combination of the basis elements for my codomain. D of 1 is 0, and that's 0 times 1 plus 0 times x plus 0 times x squared plus 0 times x cubed. So my first column should be 0, 0, 0, 0. Next one. To find out what goes in the second column, I apply D to the second basis element for my domain. So that's D of x. And the answer is D of x is 1. So I get 1 plus 0 times x plus 0 times x squared plus 0 times x cubed. So that means the second column should go 1, 0, 0, 0. Next column, D of x squared. Well, I'm not going to write them all down this time. D of x squared is just 2x. So that's 0 times 1 plus 2 times x plus 0 times x squared plus 0 times x cubed. So that is 0, 2, 0, 0. And finally, D of x cubed will be equal to 3x squared so my final column should record that. So I have 0, 0, 3, 0. Okay, there is the basis for the linear map D with respect to initial basis B and final basis B. There is a special piece of terminology we sometimes use when we're talking about the matrix of a linear map with respect to the same initial and final basis. So if you have a linear map T from a vector space to itself, like we did on the previous slide, and if you have a basis curly B of V, then if somebody says the matrix of T with respect to B, so they don't say with respect to some initial basis and some final basis, they just say the matrix of T with respect to B, what that means is the matrix of T with respect to initial basis B and final basis B. So what we would have written as T superscript B subscript B. So on the last slide, in this language, we found the matrix of D with respect to the basis 1x, x squared, x cubed. Okay. Finally, we're going to look at some examples of matrices for the identity map. So let's look first of all at a simple situation, or a simpler situation than the second one. In this case, we think about the identity map from a vector space V to a vector space V. And you'll remember that the identity map is the map that does nothing. So the identity applied to an element x of V is just the same element x again. Now let's say you take any basis, curly B, of V. And we'll notate those elements of that basis as B1 up to Bn. Well, then I claim that the matrix of the identity map with respect to initial basis B and the same final basis B will always be the identity matrix. The reason is, well, if you wanted to find the jth column of the matrix of the identity map with respect to initial basis B and final basis B, what you have to do is work out the identity map applied to the jth basis element and express that in terms of the basis B1 up to Bn. But the identity map doesn't do anything, it just gives you Bj back again. So of course that is 0 times B1 plus 0 times B2 all the way up to 1 times Bj, and then 0 times Bj plus 1 all the way up to 0 times Bn. And that is telling you what the jth column looks like. It's telling you that the jth column of the identity, matrix of the identity with respect to initial and final basis B is, well, it's all zeros except for a 1 in position J. So this matrix of the identity with respect to the same initial and final basis B, well, the first column would have a 1 in position 1 and then zeros everywhere else. The second column would have a 1 in position 2 and zeros everywhere else, and so on. So what you've got there is the identity matrix. Let's now go on and look at a more complicated example where we do not think about the same initial and final basis. So in the second example, I'm going to think about the identity map on the space of height 2 column vectors with real number entries, so the identity from r squared to r squared. And we're going to look at the matrix of the identity with respect to different initial and final bases. We'll use as our initial basis B the basis whose first element is 1, 1 and whose second element is 1 minus 1. You know that this really is a basis of r squared because we proved it when we first met bases. And our second basis will be the standard basis. So I've called that curly E. Its elements are E1 and E2. And what I mean here is the usual thing. The standard basis is that E1 is 1, 0 and E2 is 0, 1, just like we had earlier. So we're asking the question, what is the matrix of the identity with respect to initial basis B and final basis, the standard basis E? And the answer will not be the identity matrix. So again, to help us think about what's going on here, we're going to label the rows and columns. So we have a linear map whose domain and codomain both have dimension 2. So this will be a 2 by 2 matrix. I'm going to draw it extra large like this. The columns will be labelled by applying our linear map, which in this case is the identity, to the basis elements for the domain. So our initial basis, in other words. The initial basis is 1, 1 and 1 minus 1. The rows will be labelled by the elements of the final basis. So in this case, E1 and E2. So this is always how it works. The rows of your matrix should be thought of as being labelled by elements of your initial basis, and the columns should be thought of as labelled by elements of the initial basis, and the rows by elements of the final basis. So to figure out which numbers go in this matrix, we have to work out the identity applied to the first element of the initial basis. We have to express this as a linear combination of the elements in the final basis. The final basis is the standard basis, E1 and E2. So the identity applied to 1, 1, well, that's just 1, 1 again, and that is 1 times 1, 0 plus 1 times 0, 1. So what goes in this first column is 1 and 1. And similarly, the second column can be worked out by applying our linear map to the second initial basis element. So I get 1 minus 1. Okay, when you apply the identity, nothing happens, so you get 1 minus 1. And this is 1 times E1 minus 1 times E2. So let's just record these. This one was 1 times E1 plus 1 times E2. And the second one is 1 times E1 plus minus 1 times E2. So the second column will go 1 minus 1. I mean, you'll notice actually what happened here, right? All we did was we ended up writing the first basis element for B in the first column of our matrix and the second element of our basis B in the second column. That is no coincidence. It happens always when your final basis is the standard basis. So we're done. We've computed the matrix of the identity with respect to initial basis B and final basis, the standard basis E. But what if we wanted the other way round? So let's say, what about if I wanted to swap those two bases over? So I wanted the initial basis to be the standard basis and the final basis to be the basis B. So what should that be equal to? So what I will say is that what you need to do, which is you need to take the identity, apply it to, well, if you're working out the first column of this, you need to work that out by taking the identity, applying it to the first element of the initial basis, which is E1. So what you get is just 1, 0. You then need to write this as a linear combination of the elements of your final basis, which this time is B. So that has to be something times 1, 1 plus something else times 1 minus 1. And if you find those somethings, they are what goes in the first column of the matrix of the identity with respect to initial basis, the standard basis E, and final basis B. But I'm going to leave it to you to work out what those entries are, because actually there's an easier way to do this, which we will meet later on.